So the first one and the key one is something called system analyzer. The system analyzer profiles the performance and the power of your application. It gives you with a real-time chart of the CPU, GPU, power matrix, and various other matrix. So totally it gives you up to 3 dozens, that is 36 different parameters you can identify, or 36 different parameter data is provided by the system analyzer. So how do you use it? You install a APK file, you start this application on your development machine, and then you can start seeing the profile data. So some of the key metrics which is provided for the Android platform are classified under 6 different objectives or 6 different areas. That is the CPU, GPU, OpenGL, power, memory, and the device I/O. So these are specifically for the Android platform. So for the Windows platform, it varies. The other 2 applications which are part of the same suite are the graphics frame analyzer and graphics frame debugger. Graphics frame analyzer, you can use it on Windows machine or on the Android, like you can use it for the Android platform. Whereas the frame debugger is specifically only for the Android devices only. So Android applications only can be profiled or the debug is the graphics frame debugger. So let us look at a demo. Let me show you a demo on the Intel graphic analysis. So since I'm running it on a development machine, I'll be able to show you the Android image. So that is the reason I'm running a sample application on the Windows device itself on my laptop, and I'll be showing you how the graphics system analyzer and the graphic frame analyzer works. So I'm connecting to the local machine. So the moment you connect an Android device to your system, it will pop up here. So you can directly go ahead and connect to it. And it will show you which are the applications it can profile, which are the applications it will not be able to profile. Here, let me profile the cityracer.exe. So these are the different metrics which I've already loaded. So you can see the CPU load on different CPUs, what is the load from the current application. Let me add FPS also, the frames per. So you can see that as I change the size of the window, the number of frames per second also varies. So this is how you will be able to get it. You can download the data into a CSV file so that you can share it with the graphics team for further analysis, or you can save a snapshot of the current frame. You can capture the current frame and use the frame analyzer application or the frame analyzer tool to debug it further. So let me open I have captured the frame here. I will open the frame analyzer. So you can see the blue lines here. These are the draw call APIs which have been called in the application or in the particular frame. So let me So when I select the draw call API flag, it will start showing me the different values or the different metrics at that particular instance, like what is the GPU duration, how much of the units were active at this particular frame, etc. You can get the texture here. The pixel history. So these are the different things you can do with the frame analyzer. Next, let me open the frame debugger. So frame debugger, as I mentioned, it is only for Android applications. So frames captured using the Android devices can be debugged using the Intel frame debugger. So this is one of the frames which I had captured a while back from one of the Android devices, from my Android device. So now if I open this image, it will give me the complete list of all the functionalities which were to build this frame. So from the clear flag, it has various calls. So at every call, you can see what is the image which was designed, or what particular part of the frame was designed. So let me select here. So the call when the first image was designed or the first image was developed on this frame. So if I click here in this particular function call, it will help me to give more details, or it will help me with more details about this particular frame at this instance. For example, in this particular image, you can see that in this whole frame, image or this particular photo is appearing here. I can make changes to its location directly here. So if you want to debug any debug the locations, you can make those changes here. So if you see, the location has moved a bit left. In the same way, you have other options which you can do using this frame debugger. So frame buffer, let me go ahead and change it again. So you can see the location is changing in the frame as well. So this is how you can use the frame debugger to debug your particular frames and ensure that they are displayed correctly on your device. So next comes something called Intel Integrated Performance Primitives. Intel Integrated Performance Primitives are pre-compiled APIs, pre-compiled by Intel for you, pre-compiled APIs which will that the application executions or some key functionalities are completely optimized for your particular platform. It is, as with TBB, even this is available for all platforms. It is available for Windows, Linux, Mac OS, and Android. And the same APIs can be used across the platform. So it is write once, use multiple times. Also, it is future-proof and it is supported and updated by Intel. Any new changes to the APIs or any new optimizations available, you will get it. But this is not available for all the domains. It is available for some key function domains like image processing, signal processing, multimedia, audio, video, etc. And the three key optimization goals of the IPP is performance, throughput, and the efficiency. So they are optimized by Intel to such a level that this will be the best optimization available in your application. Here are some of the benchmarks with IPP. There is a function called IPPI filter _ATU_C1R. So this particular function, when it was compiled with the Intel C++ compiler, by the way, Intel C++ compiler already optimizes your code to run faster on Intel-based devices. So when this particular function was compiled using the ICL or the Intel C++ compiler, you can see that it took almost 31.8 cycles to execute. Whereas the same function, when you with Intel IPP with SSH E3 optimization, it took 721 cycles, and Intel IPP with AVX or auto vectorization extensions, it took just 5.47 cycles. So that is like 342% times and 482 times faster than the compiled code by ICL. Another benchmark, here it is the IPPS square root 32 floating point operation. So when the array length were with various array lengths between 32 and 048576, that is the length of the array, these are the outputs which is seen. You can see that the dark line which is compiled by the Intel compiler is always more, has taken more time